Right, good morning. So today is lecture 8. So you will have, we're still marking your coursework number 1, so you will get feedback by the end of this week on this. Right, so today we will continue looking at multi-user communications. We started introducing multi-user communication at the end of the last lecture. So as usual, if you have any questions, please feel free to interrupt me, right? It's quite important that you ask questions as much as possible to understand the content. So really feel free to interrupt me. Good. So today, multi-user communication, first multi-user single antenna communication, and then we're going to look at multi-user multi-antenna communications. Right. So we finished last week with this notion of capacity region, which is, if you like, generalization of the concept of capacity that you know from maybe your first course on communication, what we saw in several lectures ago, right, where we had capacity for point-to-point channels that you will see also in information theory in quite a lot of details. But here we're looking at capacity region that really characterize this trade-off between the rates that the multiple users can simultaneously achieve. And there is a trade-off that tells us that essentially if you transmit at high rate for one user, you may not necessarily be able to transmit at high rate for another user, right? And so this is what was characterized through, for instance, this example here, where we had the rate of user 1 and the rate of user 2, and the region was this area here in green, right? And the boundary of that region was that. And so as you evolve on the boundary of that region, you essentially either favor user 1 or user 2 or something in between. Now, one particular point on that region was the sum rate capacity point. So that's the point that corresponds to essentially is the point in the region, right? So if the pair of rates of use for user 1 and user 2 in that region that essentially maximize the sum of the rate of user 1 and user 2. So it maximizes this quantity. Right, so the sum of the rate of user 1 and user 2. This is actually a metric that is often used because it tells you essentially the maximum amount of information you could deliver to all the user at once. But this is not always fair, right? So this point in this example here would be here, right? That would be our sum rate capacity point. And this sum rate capacity point would achieve a higher sum rate, right, than a point that would be here, for instance, or there, right, or there, something like this. Now, this is a good example in this case because it's a point that maximizes the sum rate, but at the same time, it's relatively fair in the sense that still user rate gets a relatively high rate, and user 1 gets a relatively high rate, and user 2 also. Right? But this may not always be the case, right? So you may have rate region. For instance, here I have a rate region for user 1, user 2 that maybe looks like something like this, right? This is just example, just for you to understand. And so, for instance, here I would have maybe 1, here I would have 2, and here that would be maybe 0.1, right? That can happen. For instance, the user 1 is closer to the transmitter or the receiver, so it's closer to the base station than user 2, for instance. Right, and so the rate of user 1 will naturally be larger. So in that case, for instance, you could have rate region that may look like something like this. We'll see some example later on. So in that case here, maximizing the sum rate would end up, so this point here, so the sum rate capacity point will probably end up here. So that would correspond to the points where actually you put all your resource on user 1, and it's better to transmit at user 1 all the time rather than transmitting at any other points in that region if we want to maximize the sum rate. That would not be a fair strategy because then user 1 will be the only one to communicate in this system. Right, so in that case, you may want to evolve and maybe sacrifice a little bit user 1 rate to increase user 2 rate, maybe evolve here or something like this. Right, so this is something that we will see later on how we can do that. But the first thing is to characterize this capacity region when we have two scenarios. Let's say, for instance, we have two transmitter 1, transmitter 2, with single antenna, and I have a receiver with a single antenna. Okay, so this is, let's say I could call it user 1 if you prefer, and user 2, and I have a single receive antenna. This would be an uplink of a communication system. And then the other scenarios that we're gonna have to look at is the opposite. I have one transmitter, and this could be the base station, for instance. Right? The other scenarios would be I have one transmitter, that could be a base station, and I have two receivers, receiver 1 and receiver 2. Right, this could be user 1 and user 2. Right, that could be an example of an uplink scenario, and that would be a downlink. Okay, but single antenna system first. Okay, so let's look at that. So this is called the uplink here, right? It's called, will be the SISO, single input, single output, multiple access channels. So I call it here SISO MAC. So the MAC is the terminology in information theory, but you can really think about this as kind of uplink. So you have multiple messages that are transmitted, and you have one receiver that has to decode all those messages. Good, so what do we have here? We have K users. In general, I have K users, maybe not only 2, that are distributed in a cell. So I can have a cell like this, and I may have multiple users, right? UE1 all the way to UE2 and so on. Then I have here a base station, and I have only one antenna, and each user has one antenna. Okay, for instance. So one transmit antenna per users and one receive antenna at the base stations. And so what is our received signal here? Well, I have the transmit signals for each of those users, user Q here. I have the small scale fading of user Q. And now I have the pass loss of user Q. And I have AWG and noise, and I have receive observation. And I sum over all those K users, right? That shouldn't be too surprising to you. You note here that in the past, for point-to-point, I was really looking at this fading, the small-scale fading. I was kind of ignoring a little bit the long-term pass loss, because the long-term pass loss, when you have point-to-point, is the same for all antennas, right? When you have single antenna or multi-antenna, if you have multi-antenna systems, this long-term pass loss is actually the same for all those multi-antennas because they're kind of co-located or very close to each other. Here, actually, I emphasize a bit this long-term, this pass loss and shadowing, for the simple reason that the user could be located at very different distance from the base station. And so they could have indeed very different channel strength in general to the base station. Right, and I have a power constraint that tells us that's my power constraint of the transmitted signals at user Q, and this is denoted as ESQ, right? So this is a user-dependent power constraint, but it could be the same for all the users. Right? So in general, it could be user-dependent. Right, so if I write this slightly differently, what do I have? I can write this sum here. I can write this sum as a product of two vectors, right? So I can write the sum. I can create a vector here, C1, C uplink 1, UL is for uplink, so C1 to CK. I create one vector, that's a column vector. And I create the channels here, the channels elements. I create this, and I put this into a row vector. And now I write this as an inner product of those two, and so I have this equivalent system model. Right? So I have a vector of information here, and I have a vector of channels. Right? So this is This is slightly different from what we have seen in the MIMO case, right? Because here, when we had a SIMO scenario, or CISO, when we had a CISO scenario in single user, we had only in a single user, obviously we had only one user. If we had a SIMO case, we had U was actually a column vector, right? And we had a vector here in the SIMO, single user SIMO, and C was just a scalar. Here I have a product of two vectors here, right? So slightly different. This is a bit equivalent, if you like, to saying you want to do some form of multiplexing of multiple streams, but you have only single receive antenna, right? If you think about this in the point-to-point MIMO, it's like you transmit multiple independent streams here from different antennas, but you have only one single receive antenna to actually decode all those streams. Right. So I will try to connect this later on. I will show you how this is actually connected to some of the processing we do in point-to-point MIMO. But so this is our system model. And so I will define the long-term SNR of user Q will be essentially the power of user Q multiplied by the long-term channel gain of user Q divided by the noise. Right, so this will be my long-term SNR. Right. Good. So we're going to assume that the receiver always knows the channels of the users. This is always the case. Right. So let's look at what is the capacity region of two user scenarios first. So the capacity region is, in this two user case, will look like a pentagon. So you're gonna have the x-axis and the y-axis, R1 and R2, and then here you're gonna have a pentagon. So the pentagon is defined by those 5 corners here, and so those 3 corners here or faces actually they're coming from 3 different inequalities, right? Equality 1, 2, and 3. We'll see this in a minute. So you see that this pentagon, in this example here, this pentagon is actually the whole area that you have in this pentagon is actually larger than the area that you get if you do TDMA. So TDMA is time division multiplexing, and this is something that you may know already. So it essentially means that you transmit. You have only one user at a time will be transmitting. So either user 1 transmits or user 2 transmits, right? And so what this figure shows is actually you can have the capacity region will be larger than the rate region that is achieved by TDMA when you have only one user at a time that transmits. And so the TDMA is given by what is given by the straight line here that goes between point D and point C. What is point C? Is the rate at which user 1 can transmit when he's alone in the system, and D is the rate at which user 2 can transmit when he's alone in the system. And this line here is essentially a time sharing line that says that during a portion of the time X, user 1 transmits, and during the other portion 1 minus X, user 2 transmits, and you vary X from 1 to 0 essentially. So when X is equal to 1, essentially user 1 transmits. When X is equal to 0.5, user 1 and user 2, they use half of the resource for user 1, half of the resource for user 2. And when user 2 transmits, essentially all the time, then X is equal to 0. That's what it says. So it's actually a straight line between those 2 points, right? So that's TDMA, right? So what we have here is something larger. So how do we obtain those points? So we have we have multiple things to look at. The first one is how do we define those 3 different phases? The second one is how we achieve those different points C, E, A, B, F, and D. So the capacity region is given by all pairs R1, R2 that satisfy those 3 different inequalities. So let me explain you what they mean. So we have 2 inequalities. RQ is smaller than something. right? R with Q is equal to 1 or 2. So that means R1 is smaller than log2 1 plus, this is actually a SNR of user 1 or user Q. So I have essentially R1 is smaller than log 1 plus SNR of user 1. And R2 is smaller than log 1 plus SNR of user 2, right? What is my SNR of user 1 and user 2 is given by this, right? This is my long-term SNR, right? Multiplied by the instantaneous channel of user Q. What does that mean? That means actually the rate at which user 1 can transmit will never be larger than the Shannon expression, right? So the rate at which user 1 can transmit will never be larger than the maximum rate at which user 1 can transmit when he's alone in the system. So those are actually the single user rate constraints. So that's the rate constraint that you would have if user 1 and user 2 were completely alone in the systems, right? So what does that mean? That gives you those two expressions. Rate of user 1 is smaller than something, gives you this line here, right? And rate of user 2, this relationship here, will give you this line there. Right. So you know already that the rate of user 1 and user 2 have to be within this square. Right. Now, additionally, we have one more condition here that says that the sum of the rate of user 1 and user 2 has to be smaller than the log of 1 plus, this is a kind of SNR as well, right? It's the sum of the two SNRs. So you can view this as you have a transmission of information where the SNR is actually the sum of the two SNR of the two users, right? And what this says is that if you have a SNR that is as strong as the sum of those two SNRs, you cannot transmit information at a rate that is larger than log 2 1 plus this SNR. That's what it says. And so here, this is given by, let me change that color, sorry. That's blue. So this is this relationship in blue here. It is actually this line here. Right? The sum of the rate of user 1 and user 2 cannot be larger than the log of 1 plus the sum of the SNRs. Right. So with this, we end up with three inequalities. And we see that the last one, the blue one, actually will transform the square from a pentagon. And so we're going to lose this small corner here. That means actually this small corner will not be achievable. If you transmit at any point that is here outside of this pentagon, right, it means that for sure you're going to have errors when you do the decoding, right? Because this is not achievable at all. Right, so now we have what would we do is that if you have a point, let's say a point here in yellow, if I have a point here in yellow that is inside that region, well, I can always increase, you see that I could increase the rate of user 1 or the rate of user 2. If I increase the rate of user 1, I get to point E, right? And I get to point E here by simply increasing the rate of user 1. So, and this is still achievable. So I could get to point E without any much problem. User 1 can, user 2 would still achieve this rate here because it's on the parallel line, but at the same time, user 1 could get higher rate. Now, if you get to point E, is that a good point? Yes or no? Maybe not. You could do better than that, right? You could do better than that because what you see is that you could actually keep the rate of user 1 equal to what you have at point E, which is the maximum rate that user 1 can get. But you could move along this line all the way to point A, where actually user 2 will have a higher rate, right? So what that says here is actually if you're on this segment here, it means that you can transmit at a rate that is non-zero for user 2, right? If you're here on this segment here, you can transmit at a rate for user 2 that is non-zero and still transmit at a rate for user 1 that is the maximum So that's the rate that as if is alone in the system. So you could have user 1 transmitted as if is alone in the system, and at the same time accommodate a user 2 that will transmit at a non-zero rate, right? But between point E and point A, what is the point that you would prefer? You would prefer point A, because for E and A, both user 1 achieve the same rate at point E and point A, but user 2 would achieve a higher rate at point A than point E, right? So you would prefer evolve it at point A than point E. Now, equivalently, you could be on this segment here that essentially says that you could transmit at the maximum rate for user 2, right? Here you would transmit the maximum rate for user 2, and you would transmit at a non-zero rate for user 1, right? So if you transmit at point F, for instance, user 1 achieves a non-zero rate, but user 2 achieves the full rate as if it's alone in the systems. Now, between F and B, what is the preferred point? B would be actually more interesting because, again, you do not sacrifice user 1 rate. You do not sacrifice user 2 rate. User 2 is still the same as if it's alone in the system, but you can increase user 1 rate from point B to from point F to point B. Right. So how do we find the rate at point A and point B? So let's imagine that we look at point A. So at point A, I transmit at the rate for user 1 that is equal to its single user rate. So at point A, I essentially transmit at the rate that is equal to that. Right, that's the rate of user 1 at point A. Right. Now, what is the rate of user 2 at point A? The rate of user 2 at point A will be given. You see, this point here is the intersection between this segment here and this blue line. So the intersection between the red line and the blue line, right? So the blue line says R1 plus R2 is equal to something. And the red line says R1 is equal to something. Right, so from those two, I can find the rate of user 2 will be R2 will be the sum rate minus the rate of user 1. This is what I have here. This is my sum rate in blue. And this is the rate of user 1. Sorry, in red. Right. Okay, so what do you see here? When you do the difference of those two, you end up with this relationship. So you have the log 2 of 1 plus the SNR of user 2 divided by 1 plus the SNR of user 1. Or in other words, if you expand N2 and N1 equivalently, this will be the channel strength here multiplied by the power of user 1 divided by the noise power plus the signal power of user 1. So the signal power of user 2 divided by the noise power and the signal power of user 1. So this is actually a SINR. This is a SINR expression. This is the SINR that you observe at the receiver when you decode user 2 signal and you treat user 1 signal as noise. Okay, so here that point A will be achieved. A will have a rate right. So point A, rate of user 1, rate of user 2 at point A will be given by log 2 1 plus this, right, which is ES1 multiplied by this is 1, sorry, multiplied by uplink 1 square divided by the noise, and the rate of user 2, which will be given by that. Okay, so this is the rate of user 1. There's actually log 2 1 plus SNR, And here we have the rate of user 2, which is log2 1 plus SINR. Okay, so let me tell you roughly, and I will go back to this in a minute, but let me tell you what does that mean. That means that what you do at the receiver here, you have your base station, you have 2 users. What you do is that you decode user 2 message at point A here. You actually decode user 2 message, right? You decode user 2 message. While decoding user 2 message, you treat the user 1 message, the user 1 stream, as noise, right? So by doing that, essentially by treating user 1 as noise, you end up with a SINR when you decode user 2 streams that is given by the signal power of user 2 streams divided by the noise plus the signal power of user 1 streams. And then what you do SIC. You do successive interference cancellation. So you remove the streams from user 2 from the received signal, and then you decode user 1 streams. So then user 1 does not see any interference anymore because the interference from user 2 streams has been cancelled. And so what you're left with is just user 1 alone in the systems that will achieve a SINR rate of log2 1 plus SNR. Right? So point A here is obtained by doing SIC, where we decode user 2 streams first, and then we decode user 1 stream, right? And so that means that when we decode user 2 streams, we treat user 1 streams as noise. And this is why you have this SINR expression in the rate of user 2. What do we do at point B? At point B is exactly the opposite. At point B, I'm going to have now a rate pair that will be, again, given by the intersection of 2 lines, the green one and the blue one. The green one will now be this rate, single user rate for user 2, and the blue one will be the same here. So now I'm going to have similar expression, but the rate of user 2 here will be equal to this. So that's going to be the maximum rate for user 2. And the rate of user 1 will be equal to log2 1 plus SINR, where now I decode the first stream, the user 1 stream first, and then I decode user 2 stream first, user 2 streams after, right? So here, user 1, you decode, you decode user 1 for user 2 first. In this point here, you decode user 1 first. So both points are achieved using successive interference cancellation, right? We have only one receive antenna at the receiver, so we can not do any form of combining like we did in the MIMO case, where we were able to get rid of some interference by doing some form of combining. I cannot do that. I have only one antenna, but I can still do SIC, right? So I do SIC, I cancel the interference, but the way I cancel interference, the order at which I cancel the interference will have an impact at which point I can achieve on this capacity region, point A or point B, depending on which user I decode first. And any points here in between those 2 points will be achieved by doing some form of TDMA between those 2 strategies, between point A and point B. So that means actually X% of the time I will perform strategy A, and 1 minus X% of the time I will perform strategy B. Right, and by doing that and by adjusting the value of X, essentially you can move on any points here in between those 2. Right, Jinion, you have a question.
Yeah, hi, Professor. I want to ask is that at point A, are we using the SIC for only the user 1? We first decode the user 2 information, and then we decode the user 1 its own information at user 1, and at user 2 we just directly decode the user 2 information.
Right, so at point A, so let's imagine you have this setup here. You have user 1 and user 2, right? What it says here is to achieve the point A, what you will do is that you will decode, you will do SIC, but the receiver, you have only one receiver with one antenna. So that receiver will decode user 2 stream first. And then, so if I write this, the expression here, this one, right? So let me write this whole expression. Let me drop the pass loss for the time being and have y is the chance of user 1 multiplied by C1. Let me drop the prime and so on. And I have the chance of user 2 multiplied by C2 plus some noise. Right? So what I do at the receiver, step 1, step 2, step 1, I decode user 2 by treating user 1 as noise. Right? Step 2, so by doing this, I will have an estimate of C2 that I will say C2 hat. I decode C2 by treating C1 as noise. So this whole thing here, I ignore C1. This whole thing is just a big noise, right? That will appear in the signal to noise, the interference plus noise power. So I get C2. Then, second step, what do? I do H. I do Z. Sorry. So I do SIC. So I do SIC. And so I do Z is equal to Y minus H uplink 2. So I know the chance at the receiver, right? Minus C2 hat, right? And now assume C2 hat is equal to C2. I perfectly decoded C2, right? So I have Z is equal to Y minus H uplink 2 C2. That's now H uplink 1 C1 plus some noise. Now I'm left with a system model where I have C1 is alone in the system, does not see any interference. So here I will have a rate of user 1 that is log 2 1 plus SNR. Here I will have a rate of user 2 that will be a log 2 1 plus SINR, where the SINR comes from the fact that I have interference from user 1. Okay, so that's what's going to happen at this point A. Right. At point B, you do exactly the opposite. So at point B, you would decode user 1 first, and then user 1, user 2, and here you do SIC, but you do you decode the streams of user 2 in the second step instead of decoding the stream of user 1.
Okay, so you mentioned these steps is happened at only for the user 1 side, or it's happened both for the receiver at user 1 or user 2.
So if you want to achieve point A, you would do this. You would do this at one receiver. So you have one receiver. So you have two streams transmitted from two different users, and the receiver will do that operation. So I'm not sure I understand exactly what you mean. So that receiver will just do that operation. It will decode user 2 first, and then user 1 to achieve A. Decode user 2 by treating user 1 as noise, and then perform the SIC.
Yes. Right. So why not in user 2? You can just firstly decode the user 1 message, and then you can decode your own user 2 message at the user 2 side. And for the user 1 side, you just decode the user 2 first, and then. So
it's an uplink. So the decoding is done at the base station at the receiver.
Oh, okay. Okay. Sorry.
Right. So you have two transmitters, user 1 and user 2, and you have only one receiver, which is not user 1 and user 2, is the base station, right? So there's only two orders. Either the base station here, the receiver, will decode user 1 first or user 2 first.
Okay. Sorry, I just a mistake. It's a downlink. Sorry.
Yeah. So you see the downlink is different. So this is an uplink. So you have only two orders here, and you have to. If you change the order, you actually change those points. Now, any points here in between, right, means that during a portion of the time, you do strategy A. During the other portion of the time, you do strategy B. If you do strategy A 100% of the time, you end up with that point A here. If you do 100% of the time strategy B, you end up with that point there. Right. Okay. So that's what it means. Right. So in the general case where you have k user, now you have k rates. So you have a vector of k rates, and you start having many combinations, but the idea is still the same. So you have the rate of user 1, that is, let's say if you have k is equal to 3. Chinche, just a minute, I will come back to you. Rate of user 1, rate of user 2, rate of user 3. Right, and then you may have the rate of user 1 plus the rate of user 2 has to be smaller than something, rate of user 2 plus the rate of user 3 has to be smaller than something, rate of user 1 plus rate of user 3 has to be smaller than something, rate of user 1 plus the rate of user 2 plus the rate of user 3 has to be then smaller than something. Right, so this is what is reflected through here, is a sum over Q belonging to a certain set S, where S is actually a subset of K, whereas K here is 1, 2, all the way to K, right? So you take any subset of K. So subset here would be, in this case, is 1. This subset here is just 2. Here is just 3. This subset here is 1, 2. Here is 2. And 3. Create. Now it's become more difficult to draw, obviously, but this will be your capacity region. Good. Ginger, any question?
I have a question about the orders. You mentioned the orders when you do SIC. The orders depends on which one symbol is easy to estimate or easy to detect, or based on the power allocation, or based on the channel of the two users, the order.
So here at this stage, it doesn't. What I want to show you is that if you change the order, you will actually achieve different points on the boundary of the capacity region. Right? So if you fix the transmit power for user 1, user 2, you fix the channels of user 1, user 2, you fix the passes there, so they're located somewhere, in a certain area. You fix the power, everything is fixed. Then the question is, what is the capacity region of this system? And the capacity region is given by this, right? Now, where do you operate will now depend on which user you will decode first, right? You will get point A or point B depending on whether you decode user 1 first or user 2 first, right? If you change the power, it means actually you change ES here, right? That's your total power you can transmit. This is the total power you can transmit to user 1. This is the total power you transmit to user 2. If you change those values, if suddenly you transmit power of user 1 and user 2, the maximum power is actually is increased, then that whole region will change also, right? If it's increased, if ES1 and ES2 actually doubled, then the whole region here will actually be enlarged, right?
Oh, okay.
So for a given constraint on the transmit power, you know that the transmit power of user Q is smaller or equal to this.
Yeah.
Right, so you have a constraint. The maximum power you can transmit for user Q is given by that. You have a given realization of the channel gains. You can achieve any point here on this region, right? Any point on that region. If you increase the maximum power at which you can transmit, if you increase that, you will actually enlarge that region. How do you achieve that boundary here? How do you achieve that boundary? Is by indeed transmitting with a power that is equal to the maximum power that is allowed. So how you achieve that line here is by transmitting at a power that is actually, directly you use the maximum power that is available for user 1, and you use the maximum power that is available at user 2.
Oh, okay.
Right?
Yeah, thank you.
Okay. Good. So let's move on. Right. So this is what I was just saying, that SIC now is actually the optimal strategy to achieve those corner points, and which point we achieve depends on the decoding order. Right. So imagine now that when I do that, imagine that, for instance, I have user 1 is much closer to the base station than user 2. So I have very different path loss for user 1 and user 2, right? So that means actually the rate here, when I write R1 for user 1 is be smaller than something, here R2 will be smaller than something. Because user 1 is much closer to the base station, this point here, this line here, right, will be shifted to the right compared to this line here, right? This line here is quite low. This may be 0.2. This point here may be equal to 2, for instance, right? Simply because user 1 will be much closer to the base station, right? Now you see here that if you have this, if you operate at point A, you transmit at the maximum rate for user 1, but you have a relatively small rate for user 2. If you operate at point B, you actually lose a little bit for user 1, but not so much. You know, relatively speaking, user 1 does not lose that much. But user 2 can actually get a relatively quite large increase. For moving from point A to point B, user 1 maybe lose maybe 10%, but user 2 has his rate doubled, for instance, right? So here you see that is an example where the path loss of user 1 is essentially much bigger than the path loss, much smaller than the path loss of user 2. And so in this case here, if you want to operate the systems, maybe you would prefer to operate at point B, because actually that's maybe actually a more, maybe a fair point to operate at, right? Okay, so that would change depending on so the shape of that region now will depend on where the user located. In other words, what's the channel strength of those different users, right? If I had the opposite, if I have user 2 is close to the base station, user 1 is far away, I'm going to have something like this, right? So I have still a pentagon, but now instead of being fat like this, it's actually tall. Okay. Good. So my TDMA is strictly smaller, right? So there you transmit at only one user at a time. So you either user 1 transmit or user 2 transmit. But by doing this, you see that you get a region. The TDMA region is any point that you would achieve here, inside here. So the maximum you can achieve is on this line. And so all those points here, all those points in that region and on that boundary would not be achieved by TDMA, right? You would need to transmit the two streams at the same times and do some form of more advanced receiver in order to actually achieve those values. If you just constrain yourself to have either user 1 or user 2 transmitting on orthogonal resource or at different time, then you will have a loss. So this is TDMA. You can do the same with FDMA, right? FDMA, frequency division multiplexing. So that means actually two users transmit on two different frequencies. You would have the same trade-off, right? So this is actually the general trade-off that you have when you orthogonalize. This is when you orthogonalize the resource. You always make sure that user 1 and user 2 never interfere with each other. So either they transmit it on different time instance, they're transmitted on different frequency, they do not share the same resources, so they never interfere. This one here, the blue one, is when actually you transmit them on the same time instant and same resources, but by doing that, you actually create some interference, but it's okay. Right? If you have the receiver that can cope with this and you perform the SIC, then you can actually achieve a better performance. So you have a better better use of the frequency of the spectral. You have higher spectral efficiency, so better use of the resources. Good. So this is known for a very long time, right? I mean, we're talking about, I don't know, 50 years, something, right? Right. So this is very well known in information theory. And in wireless as well, right? It doesn't mean actually it's been used in actual systems. I will comment about this a bit later on. So let's now look at the downlink. Now I have still single antenna system, but I have now one transmitter and multiple receivers, multiple users. And so I have one transmitter with one antenna that want to deliver multiple messages to multiple users. One message per user. Okay, so now what do I have? I have a signal C that the transmitter transmit, the base station transmit. And that signal C will actually include information from different users, from the K users. So I have one transmitter that will deliver to user 1 all the way to user K. And so the receive observation at user Q, Y of Q, is given by the chance of user Q multiplied by the transmitted signals plus the noise of user Q. And now I have a transmit power constraint. I can write in general something like this, right? Let's say that the transmit power at user Q, so the expectation of the magnitude of the symbols is actually smaller or equal to the maximum power at which I can transmit, which is ES, right? I have only one transmit power constraint here because I have only one transmitter. In the multiple access, the uplink, I had multiple transmitters, I had multiple users transmitting, so I had a power constraint for each of those users. Right, okay, so same as before, I can also write this in a vector channel. So I take all those Y of Q and I can stack them up, right? I have a vector. I have a vector of noise because I have K source of noise. And I have a vector of channel gains. And now I can write this equivalently as something like this. I have a vector here, I have a vector there, and I have a vector of noise there. Now, our C prime here is now a sum of different symbols that I will transmit to those different users. So that's going to be the symbols for user 1, for user Q, and I will superimpose the different symbols of those different users. Right. So I will do a superposition of independent signals CQ prime. Right. For instance, if I have in a real system, CQ let's say C user 1, so we're going to have maybe C1 prime, could be a QPSK, and C2 prime could be also QPSK. And then you can adjust the power of this constellation. You can adjust the power of this constellation. And for instance, if you take this point here and this point there, they have different power. You sum them up, you can actually end up with a different points. So you're going to have 4 points here. On each point here, you can sum up any of those 4 points. So the sum of those two will give you effectively kind of 16 QAM, kind of. But the shape will really depend on what's the power of this constellation versus this one. And so C1 prime plus C2 prime, for instance, this could be an example. This would be C1 prime plus C2 prime. If you transmit this point here for user 1, this point there for user 2, then you actually will transmit these points effectively, right? You do a superposition of the different transmitted streams. So this is called superposition coding. Right, so what is, the question is here, what is the capacity now of this ISO broadcast channel? So what is the capacity region of these scenarios? Again, when I have AWG and noise and I have an average power constraint. Right, so let's look at, I will use something that is actually a bit reminiscent of what we did for the uplink, right? So in the, and we look at the two user first. Right? So in the uplink, you remember when we had a two user uplink, we had a point A, and that was obtained by canceling user 2 signal first. And then user 1 was left with just Gaussian noise. Okay. So let's try to do the same thing here. Right. So now I transmit a signal C prime, that is C1 prime plus C2 prime, with a certain power for CQ prime that I denote as SQ. Right. So the power of SQ has to be always smaller than the, of course, the power at which the maximum power that is available. Right. So the power of SQ, the power of S1, the power of S2 has to be always smaller than the maximum power that is available, that is ES, right? Good, and let's do the same thing as here. So user 2 signals is cancelled first. So what I will do now, I will say that user 1 will cancel user 2 signals. So now the receivers are the user side. So I don't have one receiver like I had in the uplink. Now I have two receivers because I have two users. The two users are the receiver, right? That's for a genuine comment. So if I have two receivers, then let me choose that user 1 cancel user 2 signals. Okay, so user 1 cancels C2 prime so that it will be left with its own noise, a bit similarly to what we had here, where actually the receiver was canceling user 2 signals and then user 1 was left with Gaussian noise. Let's do the same, user 1, so I have the transmitter, I have user 1, user 2, I have C1 prime plus C2 prime, and I have user 1 here. The left side of the screen always terrible. I don't know what this is due to. So let me draw this here. So I have a transmitter. I have C1 prime plus C2 prime, and I have user 1 and user 2, right? So now I see user 1. User 1 will receive C1 prime plus C2 prime. So he has to do something because the C2 prime will now create interference when he wants to decode C1 prime, right? So strategy here, user prime decodes C2 prime first, right? So if user 1 can decode C2 prime first, it will treat C1 prime its own message as noise, as interference, right? It will try to decode C2 prime and then decode his own message, decode C1 prime. So user 1 decodes C2 prime first, then decodes C1 prime. Okay. User 2 here will decode his own signal by treating user 1 signal as noise. User 2 here will decode C2 prime by treating C1 prime as noise. Okay, so let's do this strategy. What does that mean? I have user 1 cancels the interference coming from user 2 signal and then decode his own message, right? So is alone, the C1 prime will be alone, will be effectively here when he decodes after decoding C2 prime and you're left with just C1 prime. C1 prime will not see any interference, so the rate of C1 prime will be log2 1 plus SNR. What is the SNR of the C1 prime after decoding the interference? Is the amount of power that I allocate to C1 prime, to user 1 message, multiplied by the channel gain of user 1, divided by the noise of user 1. Right? That's the same as if essentially I have only user 1 that is transmitted in the system, with a power allocated to user 1 that is S1, that is smaller, that is of course smaller than the maximum power. What do I have at user 2 here? When user 2 decodes his own message by treating C1 prime as noise, right? User 2 will decode his own message by treating user 1 as noise. So you see, this is the interference that you see that is created by user 1 signal. And this is the signal strength of user 2 signal. So user 2 will decode his own message. So you have S2 here by treating the message of user 1 as noise. So that's why you have S1 there. Okay. So I have two messages to transmit. And what I'm saying is that user 1 performs an SIC and user 2 does not. User 1 performs an SIC where it decodes the message of user 2 first and then his own message, right? User 1 performs here SIC where it decodes C2 prime first and then decodes C1 prime. User 2 just treat any interference as noise. Okay, so it will treat the interference from user 1 as noise. If you do that, you get this relationship, right? Now we have to be very careful about that because doing that assumes that here, to achieve that rate, it assumes that user one here is actually able to decode, right? User 1 has to decode C2 prime. So user 1 is able to decode user 2 signal, right? That's very important. So, but the user 2 signals is transmitted at this rate, right? So that means that user 1, when he decodes user 2, is able to decode user 2 signals that is being transmitted at this rate. Right? So what that means? That means that the channels of user 1 has to be good enough to support the rate of user 2. In other words, when user 1 decodes C2 prime, the SINR of C2 prime at user 1 perspective is given by what? Is given by S2. It decodes, user 1 will decode the signal of user 2. So you see that actually I had a chance of user 1 here because I'm decoding the message of user 2, right? And I have the interference here at user 1, right? This is the interference at user 1 that is created by this own message, right? So when user 1 here decodes user 2, user 1 treats his own message as noise. User 1 treats his own message as noise. This is why the rate of decoding user 2 message at user 1 is related to a SINR expression where the interference terms is actually still the streams of user 1, but seen from user 1 perspective that has traveled through the channel 1, not to travel channel 2, right? And it decodes user 2 signal that is traveling through the channels of user 1. So if you want to transmit at a rate of user 2 that is given by this, and you want to achieve that, you want to make sure that user 1 is actually able to decode that message of user 2 at that rate. That means that the channels of user 1 here, when it decodes user 2 message, has to be strong enough so that it can decode user 2 message at the rate R2 that is given by this. In other words, it means that when you decode user 2 message, the rate at which you can decode user 2 message has to be larger than the rate at which you actually intend to transmit user 2 message. Okay, so this part here is a little bit tricky, right? So what that means is that now I have an inequality. I have this relationship and this relationship. If you put those two together, for this to hold, you need to have this relationship. So what that means is that essentially, assume the two noise power are the same. It means that the chance of user 1 has to be stronger than the chance of user 2. In other words, you transmit two messages, C1 and C2. You're looking at which user is a strong user, so which user has a strong channel gain. And then the strong user will decode the message of the other users. So if user 1, if the chance of user 1 is stronger than the chance of user 2, then indeed user 1 will decode the message of the other users. The strong user will decode the message of the weaker user, and then the strong user will decode his own message. The weak user will simply decode his own message by treating the message of the strong users as nulls. Okay, so this is called superposition coding with successive interference cancellation, right? That's the original name. This is known for 50 years as well, right? Probably early 70s. Information theory literature, but also wireless communication literature. The new name that has appeared in the past few years is called NOMA, non-orthogonal multiple access, right? So you may have heard about this, but exactly the same as superposition coding with SIC, no difference. Right. Right. So why it's called non-orthogonal is because you superimpose two messages together here, and then you perform this SIC. So actually, you do not transmit user 1 and user 2 or 2 times different instances or 2 different frequencies. This is sometimes called orthogonal multiple access, right? So the TDMA and the FDMA I mentioned here actually instances of orthogonal multiple access. You transmit on orthogonal resources. Here you transmit in a non-orthogonal manner. So you superimpose the messages and then you cancel the interference that actually this superposition has created. Okay, so a different way of looking at this is the following. If I transmit C1 prime plus C2 prime, right? And what I'm saying is that you see that here user 1 decodes C2 prime. Here user 2 also decodes C2 prime. So in other words, both users here will decode C2 prime. So this actually message here, this stream, is intended to user 2, but is actually decoded by both users, right? And user 2 will decode the stream and then retrieve the information, that's fine. User 1 will decode C2, not because user 1 is interested in C2, in the message of C2, but he will decode it in order to have access to C1 afterwards, right? To remove the interference from C2 and have access to the information included in C1, right? So, but the important thing here is that you see both users actually have to decode the message of the weakest. So you have a strong user and weaker user, strong user with a strong channel gains, weak user with weak channel gains, and both user will decode the message of the weak users. So both user will decode C2 prime. Okay, so this is a different way of interpreting this, and you can write this in slightly different way, and you will see this in coursework 3. If you do the bonus question, you will go into that. So if this message has to be decoded by both users, it means that you need to transmit at the rate that is the minimum of what is decoded. So this is the rate of user 2 that is decoded at user 2. This is the rate of the message of user 2 that is decoded at user 1, right? So if it has to be decoded by both users, it means that you need to transmit it at the rate that is the minimum between the rate that is decodable at user 2 and the rate that is decodable at user 1. So this is still the rate of the second message of C2, but it's the rate that is decoded at user 2, the rate that is decoded at user 1. What is the rate that is decoded at user 1? Or the rate of the message of user 2 decoded at user 1? This is this one. This is R21. Is the rate of the second stream, but decoded at user 1. This one here, I can write this is the rate of the second stream, but is decoded at user 2. Okay, so if you want to transmit C2 prime, you transmit at the minimum of those two, right? And if user 1 is stronger than user 2, right, the minimum will be equal to that, and that will be equivalent to saying actually that you have these conditions. So if you look at the minimum of those two will be achieved by the channels that has the weakest gain. And so essentially what we did here, and having the condition that the strong user decode the message of the weakest user, is actually the same as saying that you need to transmit at a rate that is equal to the minimum between those two rates. Right? Different way of looking at this. You can think about this when if you go into coursework 3, the bonus questions. Right, if you have any questions about this later on, yeah, feel free to ask us. Right, so in short, important thing, you have to rank the two channels. Right, you have a strong user and you have a weak user, and your strong user will be the one who will decode the message of the weak user using SIC. Now, let me finish with this before having a 5 minutes break. Now, there is one more thing here. That we had this. We say S1 plus S2 has to be smaller than ES. So you transmit a certain power S1 for user 1, S2 for user 2, but the sum of those two power has to be smaller than the maximum power available, right? So you have some flexibility here to allocate more power or less power to user 1 versus to user 2, right? And this is what we see here. Now the capacity region will be given by the union of all rate pairs R1 and R2 that are given by this, right? Under the assumption that user 1 is stronger than user 2, the chance of user 1 is stronger than user 2, those rates will be achievable for any values of S1 and S2, right? And if you change the values of S1 and S2, you will then obtain a boundary region of this capacity region, the boundary of this capacity region that will be obtained by varying S1 and S2 such that you have this equality satisfied, right? So this point here is when you allocate all the power to user 1. So S1 here is equal to ES. This point there is when you allocate all the power to E2, to user 2. And then point in between is when actually you allocate a fraction of the power to S1, fraction of the power to S2. And you can show that this is actually larger than TDMA. TDMA would be here, you transmit at user 1 or user 2, but not at the same time. And sorry, these figures are wrong. It should be like this. Right, we are in the downlink. Right, so TDMA will be strictly smaller, and actually you can show that this capacity region will boil down to TDMA if the channel strength of all the users are the same. So if I have H1 delta 1 minus 1 is actually equal to delta 2 minus 1 H2, right? If the strength of those channels are the same, then the whole capacity region will boil down to the rate region that is achieved by TDMA. If there is a large disparity of channel strength, so one user is much further away than the other user compared to the base station, then I will have the rate of user 1, that is, for instance, the user 1 is close to the base station, the rate of user 1 here will be larger than the rate of user 2. I will have here capacity region that is actually relatively large compared to the rate region that I can achieve here with TDMA. Right, so the gap here, this gap will increase as there is a larger disparity of channel strength. Okay, so that means actually, in other words, doing superposition coding with successive interference cancellation or NOMA is useful whenever you have a disparity of channel strength. If you have no disparity of channel strength, the two channels gains are the same, those two users, TDMA is sufficient. Okay, so this scheme here is known for 50 years, well understood in the academic literature, but it actually started to appear in industry in 5G, right? So in 5G, it started to be discussed. So you see, it took quite a while, even though it's very well understood. It took quite a while to actually get into industry because industry started to feel that maybe there might be some benefits to actually get into this, right? But that's for single antenna. Fortunately, systems nowadays, they have multiple antennas, and so you will see that if you do coursework 3, if you do this strategy, superposition coding with SIC, but in multi-antenna systems, the performance is not good. Good. So let me have a break here of 5 minutes, and then we're going to continue that. And of course, if you have any questions, please feel free to ask.
Hi, Professor. I have a quick question about the when you mentioned the rate for the R2 at the transmitter and for the downlink, and you mentioned that because the message for user 2 is decoded by both users, so the transmitted rate at the transmitter side should be the minimum of the rate at the user 1 and user 2. But I mean, if you mention that if you want to perform the SIC, you need to the channel for the one user it should be stronger than the other users. So why you should write the minimum for the symbol for that? You just can write the R2.
Right. So let me. So this minimum is actually a different way of writing what I did here. Right. What I wrote here. This is one way of looking at the problem that essentially says that if you want to achieve this rate here, right, you have to be very careful, because achieving the rate of user 1 here implies that you can decode the message of user 2.
Yes.
Right. But decoding the message of user 2, if you transmit the message of user 2 at a rate that is given by that, it means that when you decode the message of user 2 at user 1, you need to have a channel that is strong enough to support that rate. Right?
Yes.
That's one interpretation. Okay. And so having this relationship to hold implies that you need that.
Yeah.
Right. Now, an equivalent way of saying that is the following. So if I write the rate of if I'm user 1, so I have the transmitter and I'm user 1, and I'm user 1 and I want to decode the message of user 2. Okay. So I have R21. This is the rate at which I decode the message of user 2, but at user 1 is indeed 1 plus. Let me ignore the channel gains, the path loss, right, just to write it. So I have this. Let me assume I have the same noise. Right. And I have the rate that I want to transmit at user 2. So the message of user 2 that will I have the message of user 2 will have to be decoded by user 2. So I have a log 2 1 plus H2 S2 plus H2 S1. Right. So this is my message of user 2 that I transmit, and that has to be decoded by both users.
Yes.
What I'm saying here is that C2, you can view C2 as a form of a multicast message. So it's a message that actually has to be decoded by both users. Yeah. So if it's decoded by user 1, the maximum rate at which you can transmit C2 to be decoded correctly at user 1 would be this.
Yes.
The maximum rate at which you can transmit C2 to be decoded by user 2 would be equal to this. Now, because it has to be decoded by both, right? By both, that means actually the rate of user 2 should be equal to the minimum between R2 1 and R2 2, right? Now, what is the minimum between those two will depend on those channel gains.
Yes.
Right? If the channel gains of user 2 is smaller than user 1, if the channel gains of user 2 is smaller than user 1, that means actually R22 will be smaller than R21. In that case, R2 is equal to R22. Okay?
Yes.
And you end up with the same expression as what we had in the previous slide. If you do that, if you indeed transmit at the rate of user 2 that is equal to that, and user 2 is smaller than user 1, it actually means what you need to do, you need to do the SIC at user 1. User 1 will be the one that will decode the message of user 2.
Yes, yeah, I understand that.
Okay, if you do that, and now you have the opposite, H1 is smaller than H2, then user 1 channel is smaller than the user 2 channels, then you need to do the opposite. You need to do the other scenario, which is user 2 will perform the SIC.
Yes.
Then in that case, you will not do this where user 1 cancels user 2. You will do user 2 cancels user 1. Right? So if you want to do user 2 that cancel user 1 and you want to transmit at a rate that is equivalent to those one, but the opposite, then you're going to need the condition that the user 2 channels needs to be stronger than user 1, right? So here I'm just giving you two different ways of looking at the problem. This is one way of looking at the problem. And another way that is completely equivalent is to say, okay, but we can observe that C2 effectively has to be decoded by both users. So I need to transmit at a rate that is equal to the minimum between the rate that is supportable by those two users when I decode this message. Right? But those two are strictly equivalent.
Yeah, I understand that. Thank you.
Okay.
Yeah, and also I have another question about the superposition you mentioned in the before this page, and actually I'm a little bit confused about why you add this you add the QPSK and then it becomes the 16 QAM, and I'm a little bit confused about the superposition.
Right. Right. So when you do this here, you have to keep in mind, whenever you see the log expression, you assume that actually the symbol C1 prime, they're all Gaussian distributed. So they're not actually QPSK symbols, right? But in reality, you don't transmit symbols that are Gaussian distributed. You transmit finite constellation points. That's the way any communication systems work. So how would you implement superposition coding with successive interference cancellation in real systems? It means that you have, for instance, C1 prime is from a QPSK. So for instance, you have the rate of user 1, the rate of user 2. You can transmit the maximum rate that is this, the rate of user 2 will be there. So now you have to map this to a certain modulation and coding rate. So for instance, let's imagine that actually the constellation, a good constellation that would achieve that rate would be QPSK, and here would be QPSK. So that means that you will choose a point that is from a QPSK constellation for user 1 and a QPSK constellation for user 2. And so what you do when you sum them up, this constellation here will have, on average, will have a power that is S1, and here this one will have a power that is S2, right? And this power location here will depend on what we had here, S1 and S2, and which point you want to achieve on the region, right? So if you favor S1 over S2, S1 is larger than S2, that means actually that QPSK will be inflated, and the red one here will be deflated, will be smaller, right? So let's imagine you have a large, let me take the blue one. Let me add, so let me take two examples. Let's imagine that I have two constellations at QPSK that have the same values of S2 and S1. So I have the power allocation in this case is the same. Okay, I still have S1 plus S2 is equal to ES, but I decide actually they are the same. So ES over 2. So that means actually the energy of that constellation, average energy of that constellation here, will be the same as here. Okay, so if you take any points here, you can transmit on any points here for C1, and you can transmit on any points here for C2. Right.
Yes.
So if you take this point, for instance, and you take this point here, right, you're gonna end up with a sum of constellation points. You're gonna sum those two together, right? So in this case, you may have something. If you add this one and this one, you're gonna maybe end up with that point here.
Yeah.
If you add this one and this one,
yeah,
this one and this one, you will end up with that point here.
So there are 16 different combinations.
There are 16 different combinations. In this case, you're going to get something like this.
Okay. Yeah. So actually, the superposition is just after the modulation. The two users' messages just add together.
That's right.
Oh, okay.
But if you have different size, if this one is much larger for user 1 and the one for user 2, the one for user 2 is much smaller, right? So in that case, your resulting constellation may look like something maybe like this. Okay.
Yeah.
Right. So typically, what is happening here when you do the SIC? When you do the SIC, let's imagine that we had here. We were saying user 1 cancel the message of user 2, right? So let's imagine we have here. This is my strong user. This is my strong user. This is my weak user, for instance, right? So user 1 canceled the message of user 2. I transmit this message, for instance, right? And I transmit this message, right? So the resulting superposition one is this one. Yes, I think this one, right? So user 1 cancel user 2. What that means is that user 1 will actually decide in which quadrant he is. So he will take the received signal, and it will cancel the effect of this message before decoding his own message. So you're going to have to cancel the effect of this. So you're going to have a received observation. I don't know, you're going to have a point that maybe is here. This is your Y, your received signal, right? And your Y here will have to be, you will have a received signal that actually you're going to have to map to one of those points. And effectively, this point will actually reflect the combination of two signals, the sum of this one plus this one.
Yes.
Right? So what the receiver will do, it will essentially find out which message was transmitted and then remove the effect of the interference one before decoding his own message. Right, so this is called superposition coding. So I will actually explain this slightly later on. I think I have some slides about this, maybe, not sure.
Yes. And actually, yes. I can say that the SIC just, I think it's just to increase the rate for this communication system, because as you draw the figure, the constellation diagram, actually it will not bring some the error performance, because it has a little effect for the user to shift the shift of the user 1 message. I think it will not bring some error performance.
I mean, the error performance, I mean, obviously the error performance of user 1 here will be affected by the interference you have. If user 1 is alone in the system, it will have an error performance that would be better, right? Because it will not see the interference. Your total rate will be increased because you don't force yourself to actually have either user 1 or user 2 transmitting. You can allow to have 2 users that can transmit at the same time. This does not always give you performance gain, but in general, yes, the whole capacity region is larger, so you could achieve higher rates, right? So I'll give you some example in a minute where it doesn't give you some gain. So in some scenario, it doesn't give any gain. So
Okay, thank you.
let's go into that. Right, so so that was 2 user example. Now, if you do this for the K user, this is what's going to happen. Assume that you have an ordering such that user 1 channels is larger than user 2, larger than user K. Here I have H2. H is straight letter here, which refers to this entire thing. So it's actually a normalized, just normalized with the signal power. The noise power, sorry, right. So right, so I have user 1 is stronger than user 2, is stronger than user 3, is stronger than user 4, and so on. What is the capacity region that you would achieve? Is the union of all rate pairs, not pairs, but K tuples, right? So you have K rates, and so looking at all those rates that are such that the rate of user Q is smaller than log to 1 plus SINR. Okay, so what you see here, rate of user 1 is the strongest one. So I'm going to have S1 at user 1, I'm going to have S1, and here I have H1, and I'm going to have a P goes from S1 to Q minus 1. That's going to be 0. So here this term will be equal to 0. So the rate of user 1 will be 1 plus the SNR, right? That's a strong user. The rate of user 2 will be 1 plus some SINR, S2, and we'll see the here Q is equal to 2, so I'm going to have P equal to 1 to Q minus 1 will be equal to 1, so here I'm going to have S1. So in this case, when I decode user 2, I see the interference from user 1. User 2 is the second strongest user, so the rate will be such that I will see interference from the strongest one, right? Same as what we had here. User 2 is the second strongest user. You will see interference from the strongest one, right? So that's what we have here. Now, if you take the K is the strongest user, you will see interference from the K minus 1 strongest users, right? So if you have a user K here, you will see interference from all those users before, right? And the last user, you will see interference from all the other users. The weakest one will see interference from all the other users. Then you have a union over the sum of the power has to be equal to the total transmit power, right? So that's the same as what we had before. S1 plus S2 is equal to ES. Now I have a sum over all K. And now I have a whole union, and I can draw this whole capacity region for all possible values of SK that satisfy this condition. Right. Now there is a particular point on this capacity region, which is the sum rate capacity, that now you know what it is. Now, let me remind you the sum rate capacity when we had the MAC, the SISO MAC, right? The sum rate capacity was here, right? Any point here on this line was achieving the sum rate capacity. So any point on this line here is obtained by having multiple users transmitting at the same time, right? Whenever you're on this line here, the multiple users transmit at the same time, right? So you can achieve the sum rate capacity by having all those users transmitting at the same time. If you look at the sum rate capacity point when you have the downlink, so the broadcast channels, it's obtained by allocating the transmit power only to one user, to the strongest one, right? So the sum rate capacity will be log to 1 plus ES, the total transmit power multiplied by the maximum among all those K users. So if user 1 is the strongest one, this will be equal to H1. Okay, so you can view this directly from here, from this expression here. right? If I have rate of user 1 is log2 1 plus, let me call S1 H1. Let me, this H1 here is equal to right, this is equal to that. It's the same notation as what I have here, right, for simplicity. Same notation as what I have here, right? So this is what I call H1 now here. So I have this, and the rate of user 2 is log2 1 plus S2 H2 divided by 1 plus S1 H2. Right, so if you do R1 plus R2, what do you see? You have log2 1 plus S1 H1 square plus log2 1 plus S1 plus S2 H2 square divided by 1 plus S1 H2. Right, so that's essentially your log 2 of 1 plus do I miss something here? Right, so I have the rate of user 1 plus the rate of user 2, right? Right, I don't get confused here. Right, I mean, it shouldn't be that complicated. I don't know, maybe I have some typo somewhere. But essentially, you have to be able to show that if you sum those two, you will end up with, okay, so I think, let me write this differently. Yeah, I think it's right. So I think this is simply anyway, I don't have time. But if you write this, you should be able to show that essentially this is equal to ES, that's your sum, right? Right. And so here you have a denominator that is with H2, and here you have H1, right? So essentially you're going to have, right, you can write this equivalent. So you have, I don't know why it takes so much time, S1 plus H1, right, plus log2 1 plus ES H2 minus log 1 plus S1 H2. Right. So what you see here is that to maximize the rate of user 1 plus user 2, this one does not matter. This is already the maximum, but you have this one minus this one. And so because the channel of user 1 is stronger than the channel of user 2, this difference will be maximized by allocating all the power to user 1. Right, I think it should be something like this, but I may have some typos here. Okay, have a look at home. It shouldn't be very complicated. Okay, so that means that when you want to maximize the sum rate, you actually don't need to transmit multiple users at the same time. You transmit at only one user, the strongest one, which is very different from what we had in the Mac case, because in the Mac, we actually transmit multiple users at the same time. Now we transmit only one user. So actually, you can view this as this kind of orthogonal transmission, but this is only valid whenever you want to transmit at the sum rate capacity point. So when you want to maximize the sum rate. If you want to transmit at other points on this region, then you would actually split the power and transmit to multiple users at the same time. Okay. So in other words, that means actually your sum rate capacity, for instance, in this scenario here, your sum rate capacity, here you have the channels of user 1 is stronger than user 2. Your sum rate capacity is obtained at this point here. Okay, that's your sum rate capacity point. Right. Okay. So I talked about this. So we can show that indeed superposition encoding with SIC is optimal to achieve the whole capacity region of the SISO BC. The sum rate capacity is obtained by what you could say is a dynamic TDMA. So you transmit at only one user at a time, but that's the strongest user, right? And doing superposition encoding with SIC actually on that particular point to achieve the sum rate capacity actually will boil down to just doing dynamic TDMA. Right. Good. So then, so we end up with a gain over TDMA that is actually significant whenever we have a large disparity of channel strength. When you have small disparity of channel strength, the gain over TDMA is relatively small. So you really want to use this kind of schemes whenever you have maybe two users, multiple users that actually located at a very different location in the cell. Right, so let's move on now to the multi-antenna case. So if I have multiple antennas, it could be at the transmitter, it could be at the receiver. What do we have? So this is the general scenarios of the MIMO MAC. So this is an uplink of MIMO here would refer multiple antennas at both the transmitter and the receiver. But I could have multiple antennas at either the transmitter or either the receiver. So my system model is the same as is expanded version of what I had before. So now I have a receiver and I have multiple transmitter, but each of them has potentially multiple antennas and each receiver has multiple antennas. Right? So I have a vector here that is transmitted from a user Q that is multiplied by the channels of user Q that is now a matrix, and I sum over all the K users and I end up with a vector, right, at the receiver whose dimension is equal to the number of receive antennas that I have. Here the dimension is equal to the number of transmit antennas, right? In general, the number of transmit antennas could be user dependent, right? But for simplicity, we assume that actually they're all the same. Now, same as what we had with in the MIMO case, remember that we could define the covariance matrix of the input here of this vector, which is given by that. Now I'm going to have K of them because I have K users, and each of those users will have to satisfy transmit power constraints, right? So this transmit power constraint, same as what we had in the MIMO case, point to point, will be the trace of this covariance matrix. So the trace of the covariance matrix, the sum of the diagonal element will be the sum of the power that you allocate over all those different streams. Potentially you can transmit, right, multiple streams of information for each of those users, right? Because you will have multiple transmit antennas. So the sum of the diagonal element will give you basically the total power that you transmit from user Q, as we have done in the point-to-point case. Right, so you can write this equivalently as a kind of generalized MIMO channel. Right. I stack up those vectors, so I have K of them, and I stack them up. So I have now a gigantic vector. And I stack up the matrices from user 1 to user K, and I end up with actually a MIMO representation here, where I have a vector of transmitted symbols that includes the vector of each of those different users. So if this one is a vector with small dimensional, I transpose, so each of those small one is transposed like this, and then they actually transpose. So actually this one here is maybe CUL1 and so on, so CULK prime, right? So you stack them up into a big tall vector. Right, and I can define this as before. So now here we're going to assume that you can always, you had the CSI is known at the receiver. You may know the CSI, the transmitter also, right? In order to do some form of precoding design, or you may have to do some form of precoding. If you have multiple transmit antennas, you may have to do some precoding across those different transmit antennas. And so you may have to not only design the power location at the transmitter, but or the power location could be constrained by this anyway, but you're going to have to optimize maybe the covariance matrix would maybe a function of the channels as well. So you may know the channels of the transmitter. Right? So what I want to show you is just a simpler case, not this general MIMO MAC that can be characterized. If you're interested, you can find it in the book. But I want to show you what happens in the SIMO MAC. So the SIMO MAC is when you have single transmit antennas. So now I have here, all those ones are not vectors, but they actually are scalars, right? Same as what we had in the SISO MAC, they are scalars. The difference now is that I have a SIMO MAC, so I still have multiple receive antennas, right? So I have a scenarios now in the SIMO MAC here, single input, multiple output. So I have multiple receive antennas at the receiver, but I have each transmitter has a single transmit antenna, right? So why I want to show you that, because I want to show you what's the relationship with what we did for the point-to-point MIMO. So if you look at this, you have two transmit antennas here that are transmitted two independent streams and that are received by a receiver with multiple receive antennas, right? So this is actually very similar to what we had, you know, when we had the MIMO point-to-point. We had, let's say, multiple receive antennas, and I have multiple transmit antenna 1 and transmit antenna 2, and I was transmitting the stream C1 and the stream C2. Remember spatial multiplexing? You transmit the stream C1 and C2 that are completely independent from each other, right? And what we were doing, we had a rate that is log2 determinant I plus something like this, rho divided by NT, let's say rho divided by 2, right, H Hermitian, right? Now, essentially, you transmit now in this SIMO MAC is not much different. You have a receiver, you have two antennas, but now you have a user 1 as one antenna that transmits the stream C1, and I have a user 2 here that the stream C2. Okay. Now, the difference is that here I have a power constraint for each of those antennas, for each of those transmitters. Here I had a total power constraint, but I assume here in this example that I split the power for user 1 and user 2 uniformly, so that's when I have rho over 2, right? But apart from that, is actually the same. You transmit independent streams here. Each stream goes to individual antennas. This is actually what we have in the SIMO MAC. So that means actually all the receiver architecture that we talked about before for the point-to-point MIMO and spatial multiplexing can be reused here in this multiple antennas, multiple access channel. So you could use here a receiver that could be based on maximum likelihood, zero forcing receiver, MMSC receiver, zero forcing SIC, MMSC, SIC, and so on. Right? So what do we have? What would be the capacity region? Well, imagine that now I have, let me take the example of the two users. If I have a two user, what would be the capacity region? I have the rate of user 1, the rate of user 2, and the rate of user 1 plus the rate of user 2. What is the rate of user 1? Is log2, 1 plus my maximum amount of energy that I can transmit for user 1, ES, divided by the noise, multiplied by the norm of the channels of user 1, right? Let's say this is H1, it's a vector. And here I have H2, it's a vector as well. Log 2, 1 plus ES over ES2, multiplied by EH2, right? Okay, this is a vector again. What is the sum rate here? Well, what would be the sum rate? You can view this as what we had here, right? We had a kind of log 2 I plus this. So this is what I'm writing here. This is what I have here, right? Let me take the same notation. So I have here uplink 1 and uplink 2. So this is my uplink 1 and uplink 2. So this is the rate of user 1 and rate of user 2. This is actually the rate I have here, right? Rate of user Q. Okay. Now, you can write this slightly differently using a log expression. So you remember the log det of I plus this. If I take this and I move this here, this is a column. This would be with the Hermitian, that would be a row, right? So those two expressions are strictly equivalent, right? I can write this simply log 1 plus SNR as a log 2 det identity matrix plus the inner product, the product of a column vector with a row vector, right? Now, what is the rate of user 1 plus user 2? The rate of user 1 plus user 2 will be something like this, essentially, similar to what we had in the MIMO case. What will be H? H will now be H user 1, the uplink, and uplink of user 2. Right. So I can write this equivalently here. I can say, if I view this as a MIMO systems, where actually I have independent streams here, what is the maximum rate at which I can transmit, where I allocate a certain power ES1 and ES2, I'm going to have something like this, log 2 I plus 1 over some noise, right, of H uplink 1, H uplink 2, multiplied by ES1, ES2. This, if you like, this is my covariance matrix, right? This is the actually power allocation across the two streams, multiplied by H uplink 1, H uplink 2, H, right? Those are vectors again, right? Dimensions of the number of receive antennas. And so I can write this equivalently as log 2 I plus ES1 over this of H uplink 1 multiplied by H uplink 1 Hermitian plus ES2 divided by H uplink 2. Right, this is just, you know, multiplication of the two matrices, right? Equivalent as something like this, right? This is exactly what we have here. Okay, so that's what would be my sum rate for these uplink scenarios. And now I can compute the rate of user 2 at a specific point. So this would actually give me, again, a pentagon. I will have a pentagon. Those three expressions here will give me a pentagon like this, where I have a point A and a point B. This line here will be this one. This line there will be this one, and this line here will be this one. Now point A, remember how you get point A, intersection of the sum rate expression and the intersection of this one and this one. So I can do this relationship minus this one will give me the rate at point A for user 2. That's the sum rate minus the rate of user 1 at point A, right? The difference of the two log det there, this is a matrix, This is a matrix. If you have a -1, this will be equivalent to having actually the log2 determinant of the inverse of that matrix, which is invertible because I have an identity matrix plus something. So this is the same as log2 det of that matrix here, that matrix there, multiplied by the inverse of that. Right, and what you get is actually this relationship here. Right. So what you see here is something that is quite instrumental. You see that the rate of user 2 is equal to a log2 1 plus SINR. What is this SINR? This is something you may remember. This is a covariance matrix. This is a covariance matrix of what? Some noise plus some interference. I'm at user 2 and I see interference from user 1. This is a covariance matrix of noise plus interference when I treat user 1 signals as noise, and I had a chance of user 2 here. This is actually the SINR when I do MMSE receiver, when I want to decode user 2 streams, and I build an MMSE receiver to decode that streams by treating user 1 streams as interference. Right? This is exactly the expression of the SINR that we had before. So what that means is that I will do here MMSE SIC. I will simply design a SIC receiver where I will decode user 2 first by treating user 1 as noise, and then I will retrieve the interference that user 2 was creating, and I will decode user 1 stream. This is exactly what you're going to end up with this. So the SIC that we were doing in the SISO MAC actually can be applied into the MIMO MAC or the SIMO MAC or MIMO MAC. And essentially the processing we were doing in the point-to-point MIMO will be actually useful in this scenario as well, where you see that the MMSE SIC again plays a role here. Okay, so let me stop here for today. So what I want to highlight here is a connection essentially between what we did in the MIMO point-to-point and the processing you could do in the multi-antenna, multi-user uplink scenarios. You will see that actually in the multi-antenna downlink, things are a bit more complicated. So we'll not be able to reuse exactly things that we have done in the point-to-point case. But so that's the main message I want to finish today. I think that's it. Any questions, again, feel free to contact us. You're going to have some more class coming in the next few weeks. You have a deadline for coursework 2. Don't forget that is coming end of next week, right? 28th of February. So that's coursework 2. That's about point-to-point MIMO. And then you're going to have the bigger one, and I think the more interesting coursework, which will be the third one. What you can start reading already, because it's good that you prepare ahead, because it's a bit heavier than the other ones. Okay, as usual, any questions, feel free to contact us. And in the meantime, well, have a nice day. Thank you. Bye-bye, everyone.
Bye-bye.
Thank you.
Bye-bye. Thank you.